Today we're going to begin a new topic called conic sections. A conic section is the intersection between a right circular cone and a plane. I'll give you a couple definitions as we start off here. A right circular cone. You've probably all seen cones before, your geometry classes or lots of applications, your ice cream cones, things like this, right? Waffle cones. A right circular cone basically is a triangular shape with a circular base. It's three-dimensional. And it's right, meaning that its axis is perpendicular to the surface that circle, okay? So it's a right circular cone. You can have other types of cones. You could have elliptical cones. You could have, cones on an angle that are tipped. But right circular cones are the ones that we're interested in here. Now, for our definition of a cone, we're going to look at it a little bit differently. We're going to say there's an axis, a central axis, going through the cone. And we're going to draw a line on an angle that goes through that axis, okay? Now, the line is called a generator of the cone. And really any line that's on the cone would be a generator. Then what we're going to do is we're going to rotate this whole figure. We're going to spin it around the axis. And so this generator is going to sweep out a surface. Every resulting line at any point in time will be on the cone. And so what we will end up with is each point on this generator swipes out a circle. And the edge of each of those circles will lie on a line. Ooh, that is a poorly drawn line. A line that is at the same angle to the axis. That's better. All right. And it's going to come out in 3 dimensions. I'm only drawing a 2-dimensional projection at this point. And so the cone itself is going to be circular in 3 dimensions. And so you can kind of see, I'm trying to draw like a circular cross section up there. Same thing down here. So we have circular cross sections to this cone. And the cone technically extends indefinitely in both directions. So it doesn't just chop off at these spots. These cones extend infinitely far. This is a single cone, even though it appears to have 2 parts to it. The 2 parts are called napes. This is the upper nape and the lower nape. I suppose if this was tipped over, you could have a right nape and a left nape, whatever. It doesn't really matter. They're called napes. And the fixed point in the center is called the vertex. That's called the vertex. And of course, every line on the outside or on the edge, the surface of this cone is called a generator, okay? Because any line, it doesn't matter which line, any line could be used to generate this cone, all right? So that gives us the definition of a right circular cone. Now, with all that information, how do we get conic sections? Well, a conic section then is the intersection of a cone and a plane. All right, so let me draw another diagram that's not quite so busy. Try to draw this a little nicer. Actually, I want that axis to be solid there. Okay, so I've got my axis drawn. I'm trying to draw it so that it's kind of invisible on the inside of that cone. All right, so it's kind of hollow, you can tell. Hopefully you can see from the diagram that it's a hollow cone. Just the surface is what we're looking for. And so now if I were to intersect that cone with a plane, like a sheet of paper, but that also is infinite in size, the intersection would be different shapes. One such shape is a circle, and that's by intersecting a cone with a plane that is perpendicular to the axis. Okay, so if the axis there running through the center is perpendicular to that plane, then you will end up with a circular cross section or a circular intersection. And so the intersection is what we call a conic section, and it's a circle. So the conic sections are the intersections of the cone and a plane. So specifically, if the plane is perpendicular to the axis, the intersection is a circle. Okay. If I were to redraw that or draw another plane, if the plane goes through one of the napes but is on an angle, that's not perpendicular to the axis. So let me draw something decent here. Okay, you throw that plane on an angle, then the intersection is going to then, it's hard to draw so that it really makes sense. That's not too bad. But it's going to be an ellipse. It's basically a circle that's kind of stretched out. It's longer in one direction than it is in the other. Okay. And I always forget how to spell ellipse. E-L-L, two L's. E-S-E. I-P-S-E, yes, that's an ellipse. So that is the intersection of a plane that's not perpendicular to the axis, but goes through only one nape. Now, let me redraw a couple things here, or erase. Maybe I'll clean this one up so I can reuse this instead of having to redraw a couple things. Okay, now I'm going to, just for the sake of this illustration, I'm going to chop this cone off, even though technically it extends indefinitely. I'm going to show it as though it's hollow again. So basically the same diagram. Okay, and so on this one, again the axis is coming through. If the plane intersects one of the napes but does not go through the nape. This is kind of an interesting one. Let's see if I can get a drawing that's decent here. So if the plane intersects a nape but does not go through the nape. I might have drawn that one a little bit tilted too much. See if I can get a better drawing here. Good thing I have erasable marker as I try to do this, right? Okay, something like that. Let's again assume that this cone goes on indefinitely and so does the plane. Then the intersection of the two will be a parabola. Going in that direction, kind of along with the plane there. Okay, so it's not too bad of a drawing. It's not the best possible drawing, but it'll work. So that's a parabola. And there are proofs that these shapes are what I'm telling you they are. I'm not proving that, I'm just drawing them and hoping that makes sense. And so finally, if you take a plane and actually intersect both napes with the plane, it could be more of a parallel to the axis, or it could still be on an angle but still intersecting two of the napes. What you'll end up with, and this one's going to be really tricky to draw, so I may actually redraw on another example here, another cone. Try to do this quickly. Too bad. All right, that's one side. This one's got to go behind. And it comes out here. All right, well, that's not too bad. Something like that. There's my plane of intersection. Then the graph of this thing is going to be something we call a hyperbola. It's got a section up here. It almost looks parabolic, except it isn't. It's a slightly different curve. And it's got a second section down here. Where that's going to go through. And so you have two parts to a hyperbola. There are lots of features to each of these different shapes, these different conic sections that we'll talk about in the upcoming sections of the text. But just so you kind of have an idea, this one's called a hyperbola. And what else did I want to say about the hyperbola? That's probably about it. I guess that's it. Okay, so yeah, so we have these four conic sections. Now there are other graphs that could be found by intersecting cones and planes. If the plane goes through the vertex in some way, you could get point, or you could get a line, or you could get some other thing. So we're not going to worry about those. These are the four that we're going to really focus in on. We've seen equations of circles at times already. We're going to explore those more closely. And parabolas. We've seen a lot with parabolas already, but now we're going to go in depth into more of a geometric idea with parabolas rather than the function notation for those. And then, of course, we'll get into the hyperbolas and the ellipses coming up.